Today, we are diving into one of the most powerful and, let's be honest, most misunderstood ideas in data: correlation. We're going to break down what it is, why it's so important, and how you can start making sense of all the patterns you see around you every single day.
You know, it really all boils down to this one question. When we look at some data and see what looks like a pattern, how do we know if it's a real, genuine relationship? Or is it just a total fluke? Well, that's exactly why we have statistical tests.
And trust me, we see these potential patterns everywhere we look. I mean, researchers are constantly asking these kinds of questions. Is there a real link between showing up to class and your final grade? Or in the tech world, does this shiny new system actually make people more productive? Does pair programming really speed up a dev team? We need a solid way to figure this stuff out. All right, let's get into the fundamentals. Any relationship you find in data can be described by two main things: its direction and its strength. And as we're about to see, we also have to learn how to avoid the single biggest mistake people make: the causation trap. So first up, we've got direction. And honestly, it's pretty straightforward. A positive correlation just means that as one thing goes up, the other one tends to go up too. A classic example: the more money someone makes, the more they tend to spend. A negative correlation is just the opposite. The variables move in opposite directions. Think about it like this: more safety training at work hopefully leads to fewer accidents. And of course, there's always a third option. Sometimes there's just nothing there. No predictable link at all. We call this a zero correlation. And a perfect example of this is a person's height and their IQ score. There's just no real reason to think those two are connected in any way. Okay, and this right here. This brings us to the single most important rule in all of data analysis. Seriously, if you remember just one thing from this whole explainer, make it this: correlation does not equal causation. Say it with me. And the all-time classic example shows us exactly why this rule is so important. Let's look at ice cream sales and shark attacks. If you look at the data, they are positively correlated. When one goes up, the other goes up. But does eating ice cream somehow cause shark attacks? Of course not. There's a hidden variable, a third factor at play here: hot weather. The heat makes people buy more ice cream, and it makes more people go swimming. And more people in the water, well, that unfortunately increases the chances of a shark encounter. So the takeaway is crucial. Always ask yourself, could something else be driving this connection? So how do we actually measure these things? Specifically, if we think we have a linear relationship, one that basically follows a straight line, how do we measure it? Well, that brings us to our main statistical tool for the job: Pearson's R. Pearson's R, or if you want to get fancy, the Pearson Product Moment Correlation Coefficient, it gives you this one neat little number that sums up two things for you: the strength of the relationship and its direction. But here's the key: it's specifically for linear relationships between two continuous variables, things you can measure, like height or temperature, not things you put into categories. But, and this is a big but, you can't just throw this test at any old data set. For your result to be trustworthy, your data needs to play by 4 key rules, or assumptions. These basically make sure you're using the right tool for the right job, checking for things like a straight line pattern and making sure the data is spread out evenly. Which, you guessed it, brings us to our next fun term. I know, homoscedasticity sounds super complicated, but the idea behind it is actually pretty simple, and it's very visual. It just means the cloud of your data points is pretty consistent all the way along. What you're looking for is a nice cigar shape. What you want to avoid is a funnel shape, where the points are all bunched up at one end and then they fan out really wide at the other. All right, theory's done. Now for the fun part, the practical stuff. This is where it gets really useful. Let's talk about decoding the results. What do all these numbers that come out of a correlation test actually mean for us? So to make this really concrete, we're going to use an example straight from our source material. Researchers wanted to know, is there a relationship between how much control people feel they have over their own lives and how much stress they experience? It's a fantastic question, right? So they ran their analysis on all the survey data, and this is the first key number that popped out. The Pearson's R value was negative 0.581. So how do we unpack this? It's really a two-part story. First, look at the sign. That little minus sign tells us the direction. It's a negative correlation, so as perceived control goes up, stress tends to go down. Makes sense. Second, you look at the number itself, 0.581. Just ignore the sign for a second. That tells us the strength. And a value like that, well, that's considered a pretty strong relationship. And this table is basically the cheat sheet we use to judge that strength. Remember, for strength, the sign doesn't matter. Anything from 0.1 to about 0.29 is small, 0.3 to 0.49 is medium, and anything from 0.5 all the way up to a perfect 1 is considered large or strong. So our example, 0.581, fits right in that strong category. But that R value is only half the picture. The other absolutely critical number we get is the p-value. And in this case, the result was a p-value of less than 0.05. So what on earth is this telling us? Well, a p-value that's less than our usual cutoff of 0.05 means the result is statistically significant. Think of this as a reliability check. It tells us that it is very, very unlikely we would have found a correlation this strong in our sample if, out in the real world, there was actually no relationship at all. So in short, it's probably not just a random fluke. Okay, now for the final piece of the puzzle. This is a number that gives that correlation strength some real practical meaning. It's called R², and it tells us the proportion of variance that's shared between the two things we're measuring. And getting it is super easy. You just square your R value. So for our example, negative 0.581 squared gives us about 0.34, or as a percentage, 34%. This chart shows you exactly what that means. 34% of the change in one variable is connected to the change in the other. That other 66%, that's due to all kinds of other stuff we didn't measure. So let's just put that into a clear sentence. What this means is that in this study, 34% of the differences we see in people's stress levels can be statistically explained by how much control they feel they have. See? That really helps put the strength of that connection into a meaningful, real-world perspective. Okay, let's pull all of these different threads together and wrap this up with the key takeaway from our little explainer today. So, just to recap our journey here, we started by just spotting potential patterns out in the world. We learned how to talk about them using direction and strength, all while learning how to avoid that huge causation trap. Then, we added Pearson's R to our toolkit for measuring these things. And most importantly, we learned how to decode the results. R for the strength, P for the significance, and R² for that real-world meaning. And that really brings us to a final thought. Now that you have a better handle on how all this works, how we find and interpret these connections, what new questions does this make you ask? The next time you see a headline or hear about a new study, how's this going to change the way you think about it? What patterns in your own life might be worth a closer look? Something to think about. Thanks for tuning in.